I want to show you how to create this type of effect here. We will need to use Niagara Scratchpad, a little bit of vector math, tiny little bit of blueprints, and we will be able to create this tunnel thing. We can see some line and radius around it, kind of tunnel, and you can see these cubes are lighten up when the character is nearby. So let's start. Okay, now we are in Unreal and we are opening empty project. Let's create an empty level to start completely blank. And first of all, we want to create some Niagara system. As long as this is effect, we want to create some name for it, of course. So let's have a name and start from empty emitter. Let's give it a name of main cube tunnel, for example. We want to spawn some cubes, so let's remove this sprite renderer, add a mesh renderer, and change this gnome thing to static mesh cube. Cool. Okay, let's add spawn burst, spawn decent amount of 15,000 for start. Okay, so we spawn them in 0 position, so I want to create some shape location for that. We want to spawn them in the boxes you've seen from the video. They're spawning in the box. Also reduce the mesh size of the boxes. This is some box of boxes. We can increase the size. Okay, so let's start with creating a default line attraction force in Niagara. There is some. We want to fix the issue. It's about solve forces and velocity model to calculate all the forces. And we can see that these boxes are attracted to some line. Let's increase the force and make it negative to make them attract away from the line. And it's more looking like it's attracted from the point, not from the line. That's because the line is small. So we have start and end point of this line. Let's increase it. So the starting will be less big and the end will be higher. This looks like a thing we want, but instead of affecting on the particles inside some radius, it's affecting all of the particles we have. So let's dive inside the model and take a look at it. Actually, first we wanna copy this model to our destination, to our folder. I would advise to never change the default models, instead copy them to your location somewhere inside your folder you created. If you want to have two content browsers like I do, just check on the top of the screen. You'll see content browsers and you can create up to 4 of them. Okay, let's rename it because we don't want to be confused by the same names of the models, so we can easily find ours. I named mine as it was before, line attraction force, but I added threshold radius. Okay, let's delete the default one and take a look at mine. Remember the name and create the one here. It's a line attraction force with threshold radius. So yeah, I can see mine is on the bottom. Let's choose it. This is the one that we just copied. Okay, let's dive inside it, or we can dive inside it just double clicking it inside Niagara. It's the same thing. And we want to wrap our heads around it, have an idea of what are we going to do. So let's draw it. I have Photoshop opened already, so let's go through some math theory and draw some vectors here. What do we have? First of all, we have some line that will represent our point attraction line. I will make it red. Let's call it L. L will be line L. Okay, it's a vector, but I will not draw it here. Just know it's a vector. This black point is just 0 coordinate, 0 of the world. Let's take a green color and draw this green line. It will be our particle position. It can be anywhere in the world. This particle position is changing every frame, and for every particle is different. Next, we need starting of the line. We have it setting up in our model and end of the line. Okay, give them some decent names like S for starting and E for end. This is the parameters that we are setting up inside our module by hand. And we need this distance between this point and this line. And the distance between point and line is the vector perpendicular to vector, in our case L. So this angle must be 90 degrees. And we need this length. Let's call it X. When dealing with vectors and math, you always use right triangles. So let's find one here and use it. Build this line. It will be not that hard to find. Let's call it Y. And Y will be, oh, actually, let's call it A. It doesn't matter how we call it. It's just more convenient for me to call it A. A will be equal subtraction of p particle position minus s starting. Actually, let's make it yellow. So particle position minus starting will be our a vector. Because that's how subtraction works with vectors. You draw the line from second vector s to first vector p. So from s to p will be our resulting vector. And that's actually a, the one that we wanted. And this a vector will help us find other thing. If at any point you forgot how subtraction works or get confused by this second to first, first to second, how's that? I don't remember. Just feel free to use the internet. There's a lot of pictures that can show you how it's done. Use any one that you like. Anyway, feel free to reach out to me if you have any questions, want to ask them directly. Next thing, we can use this a vector to find this length. You could use some trigonometry for that, but actually there's a cool function for that in vectors, which called dot product. Let's call this length b, and b will be equal dot product between L and A. So dot product is projection of A into L. But to make this rule work, you need to always check if at least one of your vectors is normalized. But also you need to keep in mind that dot product is actually not a vector, it's a float, so scalar. If you ever get confused or forgot anything, just type in dot product in the internet and you'll see that there is actually cool representation for that, cool visuals. And that's what we will use. Okay, cool. So we got our b scalar float, but we actually need b vector. That's easy to find because we have b. It will be b scalar multiplied by L direction. We want to have a vector that is pointing at the same direction as L, but have the length of b. So again, to make this work, you need to normalize the L vector. You can see that I rearranged something here. That's because actually we didn't find L here because we don't set up in the model. We need to find it. And it's quite easy because we already did that operation. It's a subtraction. L will be equals E as for end minus S for start. Right now we can use the same operation to find X. It will be equal A minus B. And actually we need not the X, but length of it. There is a node for that in Unreal. If you want to know how it's done in math, it's just squared sum of all of its components, but you never use it. Back in Unreal, we can check we have start and end, and let's start making the same operation inside Unreal using a node system and Scratchpad Niagara. So this is our Scratchpad, line attraction with radius, and let's try create same thing. First is subtraction, let's check again, p minus s. P is for particle position, and S is for start of the line or super. We can see that particle position is actually not yellow line, is different. Give some annoying warning, so we want to remove that, and there's simple operation for that, and convert position to vector. You can skip this step, it will just give some annoying warning, nothing big. Got one. For our first vector, we call it A. The second one will be to find our L vector. Simple as before. Just make the same subtraction, and it's important to keep them on their place. First end, then start. And the second action is good. Next, let's go to the third one. We need to find that product of L and A to find a B. And keep in mind that, as I mentioned before, you need to normalize this L value. Normalize it means you have the length of 1 for it. Or else this projection rule will not work. Okay, we normalize it. It's simple, just one node in Unreal, and our B is found. Cool. Our B is found, but actually that's not B vector, that's a B scalar. And to find the B vector, we need to multiply this L vector on the B, but you can see I made a mistake here. I will fix that later. You need to normalize L before you put it into multiplier. Okay, closer to the end. X will be equal A minus B. the two vectors we already found. Subtraction again, a minus b, and this is our x vector. But as you remember, we don't need a vector, we need the length of it. Let's type in length. How cool is that? This is the thing that we needed to find. Let's check if this length is less than same value that we want to check it with. I will call it threshold. This will be our radius. And we take this noodle, go into this node, and I can see that it's going through all graph, which is annoying. Move it to some other place. And right now our noodles will be a bit more appealing. And remove this one because we created it on the bottom. Make it more organized. Cool. It looks pretty. It's the main thing. And we wanna make sure that our forces will be applied only if this x value is less than some value that we put in. So if it's less, then we apply these forces. If it's more, we don't. So if it's less, the forces is applied. If more than some value, we just apply physics force without any attraction. Okay, arrange this thing is the most important thing here. And let's see how cool is that. Nothing is working as always. Always when working with Scratchpad, nothing will work from the first try. Let's increase some values, tweak it, and as you remember, I made a mistake there. So it took me a bit of time to debug this stuff. This vector needs to be normalized and bam! Everything is working. Take a look at that cute little hole. We will need to check if everything is working, try some different angles of the line, try different radius, and if everything is good, we are ready to proceed to the next step. This is mostly it for Niagara, so next step we will need to be able to read some scene attributes from the character or environment, and for that there is no way around but deal with some blueprints logic. So we create some simple blueprint actor. Add a box collision to that. Visible in game, increase the thickness and its size to something like 500. This will help us to make this system interact with the world. To be able to take control over our character, we need to change the world settings game mode to something that we created. I just copied this one from third-person character and put my character into that. My character is just a copy of third-person character, so you can just put third-person character game mode there and it will work the same as for me. Okay, we need to spawn system when actor begin overlap and to deactivate it when the actor is away from the box, so end overlap. First of all this debug stuff. So I will start by drawing debug line and make sure that line that we create in blueprint will be the exact line that we want. The line that we need starting from the character location, starting from looking forward as the character to the point that character looks at. And we always need to check if the object that we're referring to is valid. Let's create is valid, add a branch node here. If the actor is valid, it means the actor is existing in the level. If the actor exists, it is valid. So if it's valid, we do action. If not, we do no action. And let's put these two vectors into line start and line end. Make it thick to see it clear and make it live some time. Let's say half of a second. And let's press play. You can see that I added some cube in the 0 world coordinate. And what we can see that when we interact with this component, our line is not looking at the character's forward vector, it's looking at the 0 coordinate. That is because our forward vector is pretty small. It's very near 0, it has length of 1. We need to add this vector to our character and we can see some small dot appearing, but it's too small still, so to make it bigger, we can just multiply this forward vector by some float value and then add to character location. And let's take a look at that. Cool, this is the line with the length of 500. We can increase it or decrease. I will put 1500. This is the line 1500. Looking in the forward of our character. Next step, we will need to spawn our system, Niagara system that we just created. For that, we can use spawn system at location node. Let's connect them, and as for location, we can use our blueprint location, not the character location, not the box location, our blueprint location, the location that we use to put this blueprint in the world. So the system will be spawned at the center of the blueprint. Cool. Let's put our system in the system template, and as we usually do, we need to check if the system component that is in the level is valid. And if it's valid, we can continue our actions. Let's promote this system component to parameter. It's not the same as system template. This one is the system that already exists in the level. This is scene component. I rename it Niagara scene component, and we try, and it's spawned. Cool. Of course, it's not taking our vector, our line into account because we didn't told it to do so. So let's do it now. We can set Niagara attributes. For this line, we need start and end. This is the vector attributes. But to set it, we need to first promote it inside Niagara. To promote, I type in read from new user attribute. And let's copy, and then copy these two nodes. Let's type in line start and line end in them. Plug in our Niagara scene component into target. And into line end, we will put line end. And into line start, we will put line start, which is our actor location. And line end is our vector's forward vector. Check if that is working inside the game. Yeah, we can see that it is working and taking our character's vector as line. But to check some different angles, I wanna destroy this Niagara when character end overlap. Let's check if it's valid. If it is, I wanna do some code, deactivate the system. Means it will stop spawning any more particles. And after some short delay, I wanted to destroy this actor, this scene component. Just destroy it means completely remove it from the scene. And let's check. Okay, it takes our forward vector. I want to match this box location with our box inside blueprint. So I copy box size, and this is again vector component of Niagara, so I can copy paste that and type in box. Oh no, type in box location here manually. Box size. Okay. Target will be the same Niagara, and the actual value will be the same as this box collision box extent. To match the size, we need to multiply it by 2. Else it will be half of the size. So Niagara must be the same size as our box component. Change these values to, let's say, 1000 and check if it's the same. And look at that. It spawns in the box and taking whole location. Next, I want to stop particles from moving outside the box. So I will kill every particle that is trying to... I use kill particles in volume, and I can see that every particle is dead. So let's invert this volume and check out. You see, every particle that is inside of this box is alive. When it tries to move out, it dies. I'm going to copy this module to prevent the particles from moving into the camera. But this time I will use sphere and give it some radius and change the location to be the same as our character. So where the line starts, the sphere will be spawned at the same location. Nice, let's check in the game. We can see that no particles is trying to break my monitor. Let's increase the size to ensure that our monitors is safe. Cool, I can see the sphere here on the bottom, but next we can try to increase the radius of this tunnel, of the threshold of the line. Let's try something like 150 and increase the particles amount, because we increase the box size, which makes our cubes spawn in less dense behavior. Write this number. Okay, that's enough for me, and I can clearly see the sphere shape. And it's too big. Let's decrease this radius to 350. We can see it here in the viewport, in Niagara viewport. Looks okay. And we also can easily add any forces we want. Let's add some curl noise force. Make these boxes less static. Let's take some small value and just take a look. Okay, they start slowly moving somewhere. Just chaotic movement is cool. We want the density to be the same for every size of the box. To do that, we need to multiply the spawn rate to box size. But we need to remember that box size is quite high value, from 500, 1000, or even bigger. So we need to divide this value by some decent amount. Let's try 1000 for starting. Let's see. Yeah, it's quite dense. Let's increase it. Increasing this number will decrease the density of the boxes inside this volume. Yeah, this looks good enough. Okay, so let's check if it's working correctly. We need to reduce the size of the box and check if the density is higher or bigger or less. The box is quite small. If it spawn every particle inside this volume, it will be too much, but it looks okay here. We can even increase this value to 5000. Better. Cool. Dense enough. Small tiny hole. How cool is that? And cool, and let's make these particles avoid character. So let's add point attraction force, make it negative, and in some radius, which we'll set here. Let's start with a big value like 750. We want two particles to start avoid our character if they inside this radius. So you can see I made another mistake here. Position to attract should be our particle's position, and I need to change attractor position here instead. But we will find out that soon. We need to set player position as our point to attract particles. Also, maybe let's decrease the radius to 500. And we need to make sure that our system is reading this character location attribute every frame, so it can be changed while playing, not only once. For that, we will need to check if the Niagara is valid, and we can set this player start variable, copy it from here, and set it here, and our attraction position will be actor location, not once but every frame. So we can see that it's not working. We can see that the size is too small. Let's increase it to have better understanding if it's working. They start to move, but they are not afraid of our character, which is not the behavior I expect. They need to respect our character, play with the values, and I can see that this attractor thing didn't help the particles to respect our character. So let's fix my mistake here and change the attractor position to our character. And they started to be scared. Cool. Let's decrease the radius and decrease the strength because it was too much, and make it a bit random. And now they're flying out of our character. That's what I wanted them to do. Let's increase the size even more. Cool, cool, cool. They're afraid. Look at these particles. Let's increase the tunnel radius here. And we have big hole here. Let's increase the box size to fit our big hole, and we are getting there. I want to play with the color, and I can see that our cubes have no material, so I created some material off screen just to have some colors on the edges of the cube. This is the simple mask, and we can see that our cubes is not the same as default Unreal cubes. So let's just fix this UV thing too much. And let's increase the contrast by adding power node. And we want to multiply this color by particles color to set this color inside Niagara. Cool, we have some blue color here. So let's set the color inside update script. Let's type in color. This is it. I want to add some color to the default one. So there's no add color in Niagara. We can add a vector. So let's convert the color to vector and add some to that. Let's bring this back to color and make it particles color. And for B value, the value that we want to add, we need to check. Okay, it's adding blue. Cool. We need to lerp this. We don't want to use this alpha. It doesn't matter. We want to lerp this vector depending on the distance from the line. So lerp here, if the distance is small, the color must be 6 in blue, and if the distance is big, the color must be 0. So we're adding nothing. Okay, and set 0 to the default color. Okay. Now we need to set our lerp factor, and for that we need to use our distance from the line, which we found using our math. It is this x length. So we can output it and name it somehow like distance from the line. So if we output it, we can use it in any model we want. We can use it in our color model, put it in alpha. Since the small value will be lightened and big value won't be lightened, because we need to put 6 in first value and put 0 in second one, and put distance from the line into alpha. We actually know that our distance is quite big. There is numbers like 500 and so on. So we need to clamp it from 0 to 1. Every time it goes above 1, it's clamped to 1. But it makes our particles not colored. So we can divide this distance to some value. Let's experimentally find it. Let's type in 50. Okay, some particles are colored, but very few of them. Increasing this value will make more particles being colored. Okay, and we see some perimeter of this tunnel thing colored. The further away, it's not. Cool. Next, we want to copy this model to make the same behavior for our distance to our character. So it's actually the same. We just need to change this distance to line to our distance to character. Distance to character is distance between particle position and our character position. So we type in distance between positions and use particle's position as first value and player position as our second value. Numbers the same. Let's check how it works. This is the tunnel that is lighting up. This is the character, and the particles are afraid of it. And the color. Cool. Looking good. We can add some final touches. You can polish it as much as you want. Go to the end. I will add some collision. Make it analytical planes. Move it to 0, like to the ground. Remove the friction. Cool. Save. And check how it works inside the game. Let's go in. Okay, they're flying on this ground. They're afraid of me. They're lightened by me, which is cool. This is the behavior I expect them then to do. We can now we can play with it as much as we want. We can add any forces. We can make this cubes oriented as we want. Let's orient it to their direction, and let's see how it will look. Also, I want to increase the box size a little bit. Let's try it out. How's it looking? Let's make it full screen, and this is the lighting boxes aligned to their velocity. Cool. Now you can create your own version of it, try different forces, different colors, and explore math to create different behaviors. Good luck!